Hey, welcome back. This is college algebra, and we want to deal with these things called log functions. So, oops, I got the wrong color pen. Let me go back here. Okay. So, anyways, we'll start with the definition. What are they? That sort of thing. They are the inverses of the exponentials. So if you remember last time we were talking about exponential functions, and here is an example of one. This is the kind of the growth function, exponential growth function. And if you look at it, you notice it passes the horizontal line test. That implies it's 1-to-1. That implies it's invertible. Okay. So this would be some sort of thing like y equals b to the x, right? Okay, so what is the inverse of that exponential function? And we know it must exist somewhere. How do we find inverses, that sort of thing? So recall finding inverses. So if you're given something like, I don't know, f of x equals 3x plus 1. So recall finding inverses, I guess I should say, finding inverses. And this would be my example. So how did we do that? Well, we said, okay, this is y equals 3x plus 1, and I switched the x and the y, so x equals 3y plus 1, and then solve for y. Okay, there it is. So 3y is x minus 1, and then you can divide both sides by 3. X minus 1 over 3, and then make sure it satisfies the cancellation equations. Okay. Now, I want to do the same baloney with this function y equals b to the x, right? So you swap the x and the y, naively just carrying about, and then you want to solve for y, just like I did in the previous example. But I don't know how to solve for y. It's like I can't like take the y root of both sides. That's not going to work. I can't like I don't know, square both sides. That's not going to work. I can't subtract something and magically get y out of the exponent. I know there exists an inverse though. Okay, so it has to exist, right? So what I'll do is just call it something. Well, let's just say this y thing, because we know it exists, this inverse function, we know it exists, let's call it log base b of x. Okay, and that's equivalent to then saying x equals b to the y. That's what it comes from. So this thing becomes your inverse function. And there we go. There you have it. So ultimately, the way you think of this thing is in terms of this x equals b to the y. Okay, so you'll see in the book the definition. So in the book, we have y equals log base b of x is equivalent to this idea x equals b to the y. Okay, so that's, you kind of have to think of it that way when you go and work with these things. Okay, so working with the logarithm, and first kind of problems, I just want to convert from exponentials into logs. Okay, so I'm going from exponential form into log form. Okay, so example, we have something like 5 to the 4th equals 625. Okay, so you can kind of try to put it into this form and then go over to this form, right? So if rewriting it, it's 625 equals 5 to the 4th. So if I put it into the logarithm here, I have some y equals log of something and then something, right? And what are those somethings? Well, the y, goes in the first box. So what is y in this context? This thing is the y, right? Because up here, look, that's the y, right? So y is, this first box is 4. Then b, what's the b value that goes in the box below the log? That's the 5, right? So it's the 5, right? That's the 5. And then the last thing, the x, the 625, that goes inside the log. So this will be 625, which doesn't fit there, but okay, there you go. All right. In the beginning, it's a little weird because you got this goes here, but it's always kind of like 5 to the 4th equals whatever inside the log. Okay. All right. And it's just going to take practice, but it's easy once you get the hang of it. So the cube root of 64 equals 4, right? Okay, I'm going to rewrite it again. So I'll have 4 equals 64 to the 1/3, right? Because if you have like the 8th root of x, that's equal to x to the 1 over a. Okay, that's one of our exponent rules. Okay, so again, if you want to go through and fill in the box, that's one way to do it. Excuse me. So anyways, it's going to be the 64 to the 1/3 power equals 4. Okay, so it's that kind of 64 to the 1/3 equals 4. Okay, so if you wish, 1/3 equals log base 64 of 4. That's how you should write it without the little boxes. Okay, let's one more. Another example. And without all the helper boxes, I'll just do this one. 8 to the y equals 300. Okay, so I usually put the log on the left side. I don't think it matters that much, but so log base something of something equals something. So it's 8 to the y equals 30. Okay, let's do one more example. 5 cubed equals 125. Right? So it'll be log base 5 of 125 equals 3. Okay, we need to be able to go in the other direction as well, so going from logarithms to exponentials. So let's look at some examples of that. Here we go. 6 equals log base 2 of 64. Okay, so it's going to go 2 to the 6 equals 64. And you could check that literally by multiplying out 2 by itself 6 times. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. So it works. Another one, log base 5 of 125 equals y. So it'll be 5 to the yth power equals 125. And you can actually solve for that y value. It's 3, right? Y is 3. So that kind of is the spiel. Let's move on to evaluating logs. Okay, just like you would evaluate, like what is 5 cubed, right? We know that it's 125. Now we want us to say what is log base 5 of 125 and figure that out. Okay, so that's kind of the game we're going to be playing here. Evaluating logs. And the question, so if, for example, they'll give you log base 2 of 16, what you're asking yourself in your brain is 2 to what power is 16? Okay, and of course, 2 times 2 is 4, times 2 is 8, times 2 is 16, so it's 4. Okay, so let's go ahead and look at some examples. I have log base 7 of 49. So you're asking 7 to what power is 49? Okay, so 7 squared, right? So you put a 2 there. And so log base 7 of 49 is 2. So another log base 3 of 1 over 9. Okay, so 3 to what power is equal to 1 over 9? Okay. You could kind of solve this, 3 to the x. 1 over 9 is the same as 1 over 3 squared, right? And then 1 over 3 squared is the same as 3 to the negative 2. So 3 to the negative 2 is equal to 1 over 9. So it's negative 2. Let's look at another example. Log base 6 of the square root of 6. So 6 to what power is equal to the square root of 6? We can rewrite square root of 6 as 6 to the 1/2. So that value must be 1/2. Right? 6 to the 1/2 is equal to the square root of 6. So it's like you're solving, in order to figure out the log problem, you have to think in terms of the exponential problem. And that's, I believe that's really what this definition is about. Okay? And even going back to my intro, you know, we know there exists this inverse, we don't know what it is. In order to figure it out, we kind of have to think in terms of the exponential, okay? The exponential function. I don't know. Okay, that's my opinion. All right, so next example, log, wrong color. Okay, so a log, where am I? Log base 3 of 1 all over root 3 equals. So 3 to what power equals 1 over root 3? Well, I can rewrite root 3 as 3 to the 1/2. And then I could rewrite 1 over 3 to the 1/2 as 3 to the negative 1/2. And so x basically equals negative 1/2. Let's look at another. Log base 81 of 9. So 81 to what power is equal to 9? And this time I mean, I have enough experience with numbers to know the square root of 81 is 9. So I could say, all right, or another way you could think of it is 9 squared to the x is equal to 9. Maybe this is a bridge too far, but let's see. So you'll have 9 to the 2x is equal to 9. And then you can kind of say 2x is equal to 1. And then x is just 1/2. Okay, so 81 to the 1/2 power is 9. Okay, or you just kind of recognize, okay, if I take the square root of 81 and the square root is kind of the same as raising it to the 1/2 power, you can think of it that way. Okay, and then some easy ones here. Log base 11 of 11 equals, so 11 to what power equals 11? Well, it's just the first power, right? Because this is 11 to the 1. So another one, that's easy. Log base whatever, we'll say 6 of 1 equals what? So 6 to what power equals 1? And 6 to the 0 power, right? So this will be 0. And that's about it. Okay, so we have basic properties of exponents, like and I kind of went through a couple. There's the rule for the quotient rule, I guess, of exponents, where you can move the 3 squared to the numerator and just change the sign of the exponent. Anything to the 0th power is equal to 1. Okay? There's another exponent rule. We have similar rules for the logarithms. Okay, so we'll just label those as basic properties. Okay. So the first one, log base b of b is always going to be equal to 1, right? So you're asking b to what power is equal to 1? Oh, sorry, b to the, b to the what power is equal to b? Okay, so that's just 1. Let's look at another. So log base b of 1 equals what? So b to what power equals 1 this time? So that's just the 0 one. Another one, log base b of b to the x. that just equals x. And this is the cancellation equation. So basically you're dealing with two inverse functions. One function is log base b of x, and the other guy, g of x, is b to the x. So if you go f of g of x, you have log base b of b to the x. And because they're inverse functions, that's just going to equal x. Likewise, if you have b to the log base b of x, that will give you x as well. It looks a little funny, but all it is the cancellation equations in reverse then, right? Because this would be then b to the log base b of x, and because they're inverse functions, that's just going to equal x as well. Okay. Okay, so you'll see examples in the homework, like figure out 7 to the log base 7 of 23. Okay? And what you get out is just this 23. It's like these two things cancel each other, and you just get 23 out. And that's going to come from this law here, this D, part D. Okay, the next part then is what do these look like? So we want to look at the graphs. Now that we can evaluate them, we are going to do a table of values. And then we'll be able to get our answer. Well, we're not even going to go that way. What we're going to do is graph the exponential and then rotate about the line y equals x to get the log, the inverse of the original. So, for example, if you have f of x equals 3 to the x, its inverse, g of x, will be log base 3 of x. Okay? So all we need to do is really graph 3 to the x, and then we'll be able to do a rotation and get log base 3 of x. Okay, so go -2, -1, 0, 1, 2. 3 to the -2 is the same as 1 over 3 squared, which is 1 over 9. 3 to the -1 is the same as 1 over 3. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. Okay, so I'm going to graph that. 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, so -2, 1/9. I put that maybe in blue or something. -2, 1/9. -1, 1/3. 0, 1. 1, 3. And then 2, 9. Okay, so that's our exponential growth function. I'm doing a very poor job of drawing it. There it is. Okay. And then I need to rotate that thing around about the line y equals x, okay, to get the inverse. Okay, so you could literally rotate it, or what you could do is just swap the x and y coordinates from the other table. Okay, so if this is f of x equals 3 to the x, then the table for g of x, which is equal to log base 3 of x, is just going to be the same table, but with the x and y coordinates reversed. So you'll have 1/9, comma -2, 1/3, comma -1, 1, 0, 3, 1, 9, 2. Okay. And then you could graph that, or you could just visually kind of pull it off as well. Okay. I'll go ahead and graph the points. So 1/9, -2. 1/3, -1. 1, 0. 3, 1. And then 9, 2. Okay. So it's going to look like this. Kind of. Okay. So it's going to get really, really super close to the y-axis, like that. Okay, so the red graph is a graph of a logarithm. So in general, what are the characteristics of the logs then? Okay, so section 5, sort of the characteristics of logs. So first, the domain in the range. So these will just be the opposite of the exponential function. If you remember, the domain of the exponential function was negative infinity to infinity. So the range of our logarithm is negative infinity to infinity. And then the domain is the range of the exponential. And the range of the exponential was 0 to infinity. Okay? And that will be the domain for the logarithm. Okay, there's no y-intercept, but there is an x-intercept. And the x-intercept is going to be at 1, 0, which you can see on the graph above. Okay? So there's the old x-intercept, which would be the same for sort of non-translated logarithms. What else is there? The overall shapes. Okay. So the one we were just looking at is the most typical, and it looks like this. And that's when the b value is greater than 1. If the b value is a fraction of some sort, in other words, between 0 and 1, it'll kind of look like this. Okay. You don't see that very often, but in your work, in your homework, you're probably going to have to do 1 or 2 of those. Then finally, if you remember the exponential, it had a horizontal asymptote. This one has a vertical asymptote. So vertical asymptote, which of course you can't see as it sits, but it's on the y-axis. Okay. It's right there at x equals 0. Okay. Okay, so graphing, one thing you could do is just a table of values and then do a rotation. Another thing you could do is use the translations. Once you know the basic characteristics of the logarithm, you can graph by just doing shifts by translations. Okay. So an example of that, let's say we want to graph g of x equals log base 2 of x plus 2. Okay, so if you add something on the inside, that's going to shift it to the left by 2. Okay, so let's take a look at what we got. So first I'm going to kind of get the table for 2 to the x. Okay. That will allow me to graph log base 2 of x. And then I'll do shifting to get to log base 2 of x plus 2. Okay, so negative 2, negative 1, 0, 1, 2. 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. And finally, 2 to the 2 is 4. So for the other table, the log table, you just switch the coordinates. And then we can come over to our graph and take care of that. 2, 3, 4, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So I'll put log base 2 of x in red. So 1/4 negative 2, 1/2 negative 1, 1, 0, of course, 2, 1, and then 4, 2, and there's log base 2 of x. Okay. Then I have to shift all those points over by 2, so I'll do that in blue. 1, 2, 1, 2, 1, 2. 1, 2, 1, 2. So it'll end up looking like this. Yeah. Okay. And one thing about this is the asymptote also moves. So if you remember, the exponential version of this, when you move up or down, you got to move the asymptote. Now, when you move left to right, you have to move the asymptote as well. So the original asymptote there in yellow for log base 2 of x, and then that'll move over by 2 to this new position. I don't know, let me put it in sort of a whitish color. So that'll be sitting right here for our new asymptote. Okay. And that's the deal, that's the spiel. Okay. Right, so the new vertical asymptote is at x equals -2. The old asymptote is at x equals 0. Okay, so there's the spiel. Okay. There are issues with the domain of log that come up. Before, when we talked about domain, so recall domain issues. The domain is a set of all real numbers except the numbers that cause division by 0 and negatives under a radical. Okay. But now we're going to have a third thing to watch out for. Basically, we need to make sure that whatever's inside the log is greater than 0. Okay. And if you look at the domain of the log, that's kind of the spiel, right? It's all real numbers greater than 0. You can't take the log of 0, but anything above 0 is fair game. Okay. So section 7, then the domain of the log. We have that given this function f of x equals log base b of g of x, we need to make sure, or we require, that g of x is greater than 0. Okay. So, for example, this problem, we have f of x equaling log base 5 of x plus 6. We need to make sure that x plus 6 is greater than 0. In other words, we need to make sure that x is greater than -6, and that means the domain is going to go from -6 to infinity. Okay. A little harder one, let's get another one, is something like this guy. F of x equals the ln of x minus 7 squared. Okay. So again, I need to make sure that x minus 7 squared is greater than 0. And then what is this? This is a polynomial inequality, right? We've learned how to solve these, so we can do this. You factor that thing. X minus 7 squared is the same as x minus 7 times x minus 7. Set it equal to 0. Get your boundary point, and then you go over and do your number line with your test values, your signs, and your conclusions. And let's do this in red. So I'll try x is 0. If you put 0 into this equation here, or this expression, rather, you'll get -7 times -7, which is positive, so that will be greater. And then let's try x equals 8. So if you put 8 in there, you get you'll get a positive times a positive, which is positive. So again, that'll be greater. And we want the intervals where we have the greater than symbol. So it's both these intervals. But we don't include the number 7, okay, because of the inequality type. So if there was a line underneath the inequality, we would include 7, but we can't. And if you put 7 in there, you'll see 7 minus 7 is 0, 0 squared is 0. The ln of 0 is not defined. Okay? So at the end, our domain then is going to be the, well, everything except 7, right? -infinity to 7, union with 7 to infinity. Okay? Okay, so there's a harder one. We don't use like every logarithm base in the universe, okay? In particular, there's only really 2 kinds of logarithms we care about, and those are the common and the natural logs. Okay, so first off, the common log. And that is log base 10. So log base 10. And we use it so much that we have kind of a, if you don't see base 10 written there, it means it's base 10. Okay. Okay. And then an example, log of 1,000 equals what? So you're asking 10 to what power equals 1,000? And I think that would be 3. So x equals 3, so 3. Okay. Then the other kind of log we have is the natural log. Okay, so in that case, it's log base e, which is that natural number e from the last section. That's like 2.7 or 2.17 or whatever. It's like the number pi, right? This has a shorthand notation ln, okay, of x. So if you see ln of x, what they mean is log base e of x. Okay, so for example, one that they expect you to have memorized, the ln of e is equal to what? So this is saying e to what power is equal to e. And well, clearly that's 1. Okay. Some other examples. Another one that you need to have memorized if you keep going through math. E to what power is equal to 1? Well, that's 0. Okay, so if you're going to keep taking math and you take calculus, this needs to be memorized. Okay. Okay. Some other examples. The ln of e to the 7. So what does that equal? So e to what power equals e to the 7? That's easy. That's just 7. Another one. E to the ln of 300. This is the cancellation equation because e to the ln of x is equal to x, right? So this will just be 300 from the cancellation equations. And I think that's about it. That'll do us for this section. Okay. Thanks for watching, and we will see you next time.